Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello. All right, this is lesson 12. We are now in topic C of module 2, moving right along. Lesson 12 says, what are similarity transformations and why do we need them? Classwork opening exercise. Observe figure 1 and 2 and the images of the intermediate figures between them. So just picture this getting bigger and rotating. All right, figure 1 and 2 are called similar. What observations can we make about figures 1 and 2? Well, the two figures look alike in terms of shape, but not size, okay? So this is a rotation, and if you just rotated it, figure 1's backwards, so it's also a reflection. But the shapes are similar, but they're not the same size. Okay, so by definition, a blank is a comparison of a finite number of dilations or basic rigid motions. The scale factor of a similarity transformation is the product of the scale factors of the dilations in the composition. If there are no dilations in the composition, the scale factor is defined to be 1. So I kind of have a problem with this diagram here. We can't just simply dilate this and get this because this is a backwards J if you rotated that. So let me show you. So if I do a screenshot of these two figures like so, and I put it here. So there's the copy of that. It's a little bit larger. So let me bring it back. And I rotated it. Yeah. So it is not just a dilation rotation. It's also a reflection. Okay. But anyway, a blank or blank. So the answer to these is a similarity transformation, or, and it says it right here, by the way, the scale factor of a similarity transformation is a product of scale factors of the dilations in the composition. If there are no dilations in the composition, the scale factor is defined to be 1. Another way of saying that simply is a similarity. So there's a similarity transformation or just simply a similarity. So here's the definition. Two figures in a plane are blank if there exists a similarity transformation taking one figure onto the other figure. And two figures in a plane are, whoops, missed my, where is it? Okay. There it is, similar. Two figures in a plane are similar if there exists a similarity transformation taking one figure onto the other. So this transformation would actually be a rotation and a reflection. Okay, and that's page 1. Page 2 brings us to an example and a table of information. So I'm just going to give you the fill-ins for this, and then we're going to move on. All right, so here we go. Definition. A similarity transformation, or just simply similarity, is a composition of a finite number of dilations or basic rigid motions. The scale factor of a similarity transformation is the product of the scale factors of the dilations in the composition. If there are no dilations in the composition, the scale factor is defined to be R equals 1. Okay, these are things we already know. And then if I move over here and get to this one, it also should say two figures in a plane are similar if there exists a similarity transformation taking one figure onto the other figure. And for characteristics, we have similar figures should look the same, but one is a different size, flipped, rotated, or translated relative to the other. Okay, so we can have any one of those three transformations. And here's an example of similar. Smiley face, smaller smiley face, both circles. The eyes are circles. And the mouth is an arc. So if I were to check this, I would draw a segment from the corner of the mouth to the corner of the mouth, from the corner of this mouth to the corner of this mouth. And when I do that, I would find the point of dilation, which is somewhere around here. We could also have used the eyes. Okay, so there you have it. So a non-example or a counter example would be taking a circle and then squishing in its head like this. And that is called an ellipse. And then therefore the eyeballs, which were circles, are now elliptical. And this arc would be an arc of a circle. And this arc is an arc of an ellipse. So if I did the same thing I just did with the circle, let me make the line thinner this time though. And if I drew a segment from the corner, pick the right command, it might work. All right, it's thinner. So if I choose from the corner of the mouth to the corner of the mouth like so, and then I choose from the center of the eye through the center of the eye like so. And then if I chose the corner of this mouth and the corner of this mouth, notice that these two intersected here, but the eyes will not intersect at this point, and that therefore tells us that the dilation was not of similar shapes. Okay, so if I continue doing that, and I chose like the top of the head to the top of the head, that's going way out there. And if I chose from the chin all the way down to the chinny chin right there, all right, so these are getting further apart. So the center of dilation for the actual shape would have been over here, but the center of dilation for the mouth, it would be right here. So the figure's not similar. All right, hopefully that makes sense to you. So now we have an example one. I've already begun it because it was a lot of work creating these pieces to get them to fit and line up. And anyway, here's example one. Figure Z prime, the green one down here like so, is similar to figure Z, this green one. Describe the transformation that maps Z onto Z prime. So the first thing we had to do was find a dilation. The first, from Z to Z1 is a dilation. So if I chose this point right here, and then I chose the end of this arc going through the end of this arc like so, and then I chose the end of this going through the end there, then we find a point of dilation. And that point of dilation is right here. And that would be our O. Okay, that would be our O. All right. So there is O from dilating this down. So it's a dilation where R is less than 1, but greater than 0. Okay, so my pen whacked, so let me fix it. All right, let me rewrite that because it's messy. See if my pen's working now. So R is less than 1, but greater than 0. Because it's Z sub 1 is smaller than Z. Okay, so then we have this dotted line, L, or dash line. And if I took and, let's use blue this time. No, not blue, purple. And drew a, struggles are real. All right, how about this way? Purple, thin, from here to there. So I'm off a little bit. This should be the same distance. This should equal this. All I'm trying to explain here is that this was reflected across L. This should be a little bit further away. So I suppose I could do that, but then I'm going to lose it because it's going to go in behind. It should be down farther like that. Okay, and then when I take this and drive it down there, this distance should be the same as that distance, and then this distance to here is the same. What I'm saying is this is a reflection. Z sub 1 was mapped to Z sub 2, so let's call it that. This diagram down here is Z sub 2. And then I take it's the same size as this one. So if I draw a vector, what color could I use? Orange. So if I drew a vector from here to there, okay, that vector direction and distance should be the same for every point. It's close. It was very difficult to make this diagram. All right, but you get the idea. That is the direction and the distance it went to map Z2 onto Z3. And then finally, Z3 mapped onto Z prime would be a rotation around, and this would land right on top of the green one. Okay, so let's sum that all up. So we would say figure Z maps to figure Z prime by first dilating by a scale factor of R units until the corresponding lengths are equal in measurement, and then reflecting over line L to ensure that both figures have the same orientation. Next, translate along a vector so that one point of the image corresponds to Z prime. That would have been this one. Finally, a rotation around point A, and I didn't label that A, so I will. This is point A, rotating about the point that they share. Actually, it says not point A point C. So this is a point C. Finally, a rotation around a center C of degrees theta, Greek letter that we name angles, orients figure Z so that it coincides with figure Z prime. Okay. Okay, page 3 brings us to some exercises with 3 exercises. Pause the video, see if you can do these. They're very similar to what I did on the last page. It says, okay, so I'm assuming you paused this, did these, and are just checking. Exercise 1 through 3. Figure 1 is similar to figure 2. Which transformations compose the similarity transformation that maps figure 1 onto figure 2? So if I look at R to R1, that is definitely a dilation. This is bigger than this. So if I take and I show my lines from, say, the corner here through the corner here, and let me scroll up. I might need to make that a little longer. So we're taking the top right corner of the R and going like so. And then we're going to do it again. And this time I'm going to choose right in maybe this corner here. So when I do that, then we only need 2 points to find our point of dilation. But if I do one more from the little center there of R to there, right where that R goes, curves in and then hooks out, that's called a cusp, right through that cusp. That will bring us to our O. There's our center of dilation, making this little R figure 1, this big R sub 1 R. So that was a dilation with R greater than 1 because it got bigger. And then if I take a line segment, let's make it dashed, and I draw it down like so, and then move it in between. Come on, man. Hello. Come on. All right, there we go. Struggles are real, kids. All right. there is a line of reflection, and R sub 1 flips over to figure 2. So what I would say is, first, dilate figure 1 by a scale factor with R greater than 1 until corresponding lengths are equal in measure. So you would do that until, where are you? Right here. The sides from, say, here to here equal here to here. All right. And then reflect over a line L so that figure 1 coincides with figure 2. So that's basically what we're doing here. So in this situation, it says figure S, this ice cream cone here, transforms to S prime down here. Well, how did we do that? Okay. Well, again, it's a dilation. And it's a dilation, and we already know where O is just by looking at it. Our O is right here because S and S sub 1, this side here is shared. And so all I did was, or all that happened, I should say, I didn't do it. All that happened was, choose the right command, man. All right. So if I put that there and go to there, all that happened was we dilated it out larger. So it was a value greater than 1. Okay, but less than, this little segment here is just a portion of this segment. If it was, say, 1/5, that'd be a 20% enlargement. So R would equal 1.2, something like that. And then doing the same with all these pieces from this point would make it S sub 1. So we enlarged it until this segment right here was the same length as this segment here. So that's how we decide how to enlarge something, until it matches the image. So the pre-image has to be enlarged until it matches the size of the image. And then it was a rotation this direction to get S sub 1 to land onto S prime. So let's sum it up. First, dilate S by a scale factor of R greater than 1 until the corresponding segment lengths are equal in measure to those of S prime. They did not say that O, the center of dilation, was the point of the cone, but it is. Then S must be rotated around center C at degrees of theta so that S coincides with S prime. Okay, so now we have a paper clip, and it says figure 1 is similar to figure 2. So figure 1 is this one here, going like so. And then F sub 1 is a rotation of negative 90 degrees. All right, so if I took and put a point here, to get it here, I'd have to rotate this direction, and that is a 90-degree, what is wrong with my pen today? A 90-degree clockwise rotation. That's a CW, by the way. So we rotate it 90 degrees about its center, which should be right about here. So rotate that so it ends up there. And then we would take a line segment, I'll just borrow from that one, and put it there. And then it's reflected across. And boom, we are done. So what's our explanation on that? It is possible to only use two transformations, a rotation followed by a reflection. However, to do this, the correct center must be found. The solution image reflects the approach, but students may say to first rotate figure 1 around center C, okay, by 90 degrees in the clockwise direction, then reflect figure 1 over a vertical line L. Finally, translate figure 1 by a vector so that figure 1 coincides with figure 2. Okay. All righty. So there you have it. All right, page 4, example 2. Show that no sequence of basic rigid motion. So this one we're trying to show no sequence of basic rigid motions and dilations takes the smaller figure to the larger figure, take measurements as needed. So if it says to take measurements, then I get my measuring stick, which is called a ruler. All right, so if I measure this A to B, segment AB, come on, segment AB is about 4 millimeters. So I will write that over here. So I would say the length of AB equals 0.4 or 0.4 centimeters. Yours would be different on paper, of course, because when I create this, it might scale it. And then I rotate this around. And obviously, if I were to rotate this 90 degrees counterclockwise and then dilate it, A would end up at C, B would end up at D. Hopefully you can visualize that. So now I'm going to put my 0 on C, and CD is 1.5 centimeters. So CD equals 1.5 centimeters. All righty. All right, so to find the scale factor, we are going from small to big. That means R is greater than 1. CD is greater than AB. So to find our scale factor, R would equal the length of CD divided by the length of AB, which would equal 1.5 divided by 0.4. And 4 goes into 16. So if this was 1.6, it may be, but just because this is not so accurate, 4 times 4 is 1.6. So R would equal about, let's put about, R would be about 4, our scale factor. Okay, so now we need to measure something else. So we have a scale factor that takes AB to CD, a scale factor of 4. Now if I measure from A all the way over to this point, let me get my pen. This point right here is a distance of 3.1 to 3.2. So let me call that, let's see, they use CD, A, B, C, D, E, F, and call this G, G, H. Okay, so I want to know AF. That doesn't even look like an F. F. This is F. This is H. So I want to measure AF. So I would say the length of AF equals, and I want to measure its image distance of CH. So then I put CH equals. And then I would measure from A to F, and it looks like 3.3 centimeters. And then take my ruler and measure C to H, and it's 6.6 centimeters. So if I want to know R, the scale factor that would get CH from AF, I know it's enlarging, so I know R is greater than 1, then the greater number has to go on top. So the length of CH compared to the length of AF will give us CH divided by AF, which equals 2. So we have a scale factor of 1 that gets AB to a CD, and then a different scale factor getting AF to CH. We can't have 2 different scale factors, so therefore It can't happen. So we say a similarity transformation that maps the small outer circle to the large outer circle would need to have a scale factor of about 2. A similarity transformation that maps the small line segment AB to the large line segment CD would need to have a scale factor of about 4. So there is no similarity transformation that maps a smaller figure onto the larger figure. Okay? And now exercise 4.5 wants you to do the same thing. So you would measure from C to D and Y to Z and A to B and X to W. Obviously, this is a rotation and a dilation maybe. I shouldn't say obviously. It's obviously a rotation. Rotated about, I don't know, 35, 40 degrees in the clockwise direction. But then if these are proportional, like up here was not, then it would be a sequence that would take the measures to ABCD or ADBC ellipse to WZXY. All right, so just to speed things up here, I'm not going to go through it like I did the example. A similarity transformation that maps segment AB. So what they did was took the measurement of AB, which is here, and compared it to WX. It would have a scale factor of about approximately 2/3. So for the red, R equaled approximately 2/3. Okay, 2/3 is less than 1, AB, WX is less than AB. Okay, but a similarity transformation that maps the small segment CD, which is here, CD is here, mapping that onto YZ, which is there, would need to have a scale factor of about 1/2. So in that situation, R equaled 1/2 for the blue. Since our R's are not equal, there is no similarity transformation that maps a large figure to the small figure. Okay, done. Number 5, what purpose do transformations serve? Compare and contrast the application of rigid motions to the application of similarity transformations. So let's wrap this up. We use all the transformations to compare figures in the plane. Rigid motions are distance preserving, while dilations, integral to similarity transformations, are not distance preserving. We use compositions of rigid motions to determine whether two figures are congruent, and we use compositions of rigid motions and dilations, specifically similarity transformations, to determine whether figures are similar. Page 5 brings us to the end of lesson 12. Review the lesson summary and go to your problem set.